The report of a European Commission on Radiation Protection titled Cosmic Radiation Exposure on Aircraft Crew measured the exposure to radiation on 8 international flights from Madrid using several different methods for measurement. Data for 2 of the methods are given in the accompanying table. Use this data to test the hypothesis that there is no difference in mean radiation measurement for the 2 measures. Use alpha equal to 0.05. So we have collected data on 8 international flights, and we are testing essentially 2 populations. Population 1 is using method 1 for radiation exposure, and population 2 is using method 2. And we're trying to find if there's a difference in those measured values between the 2 methods. In this particular type of test, although we are testing 2 populations, there is sort of a connecting agent between the 2. In other words, the flight. On the same flight, under the same conditions, method 1 is being used at the same time as method 2. So through the flight, we are able to connect a data value taken from one population to a data value taken from another. Interesting thing here is that we can go ahead and run a test, but not in comparing the averages between 2 populations, but finding the difference in the data values and then the average of those differences. So what I'm going to do is I'm going to subtract each one of these pairs of values, and I've decided to go ahead and take the values in method 1 and subtract the values taken in method 2. And the values I get for that are negative 6.9, 2.7, this one's positive. Notice that if I'm taking a larger value from a smaller one, that ends up being negative, and I want to put the negative there. So my 27.5 subtract 34.4 is a negative 6.9, but 41.3 being larger than 38.6, subtracting them gives me a positive 2.7. 3.5 subtract 3.5 is 0, and then I get a 2.4. A 2.6, negative 3.7, a 0.2, and negative 3.2. Now what I'm going to do is I'm going to calculate an average for those differences, and that is given the symbol D bar instead of X bar. I mean, I've collected this sample data, so I'm getting a sample average, but in this case I'm getting comparing 2 populations pairwise, and I'm calculating an average on those differences, and I'm going to call that, instead of X bar, D bar, the average of the differences. And when I add those 8 values up and divide by the total, I get a negative 0.7375. And I'm going to also calculate the standard deviation, which I'm going to call S sub D. Although I can do this by hand, I'm going to go ahead and use my calculator to get the standard deviation. And this turns out to be 3.526. Now I'm going to run a test on these differences, and I'm going to define mu sub d as the population average difference between the two methods. And the test, the problem says to test the hypothesis that there is no significant difference in mean radiation measurement for the two measures. So we are going to assume that there is no significant difference. In other words, the average is 0. The difference between the measured values from each method that we took average out to be 0. And we're going to test that. So we're going to see if there's enough evidence to show otherwise that mu sub d is not equal to 0. And so the very first step of setting up this test is to establish the null and alternative hypotheses. Notice that we are now running a one population test instead of two populations. We are testing two populations, but we are able through the flight to match the values from one population directly to corresponding values of the other, and then test just the results, the differences. So we're really just testing one sample of differences, and we're running a one population test. So this kind of test goes back to something we were doing prior to this chapter. And the first step then is to set up the null and alternative hypotheses. The second step is to look at the sampling distribution. And we're testing at 0. Our alpha value is 0.05, so we're going to split that. This is a two-tailed test. So we have 0.025 in the upper tail and 0.025 in the lower tail. Our standard error, which I'll call S sub d bar, is going to be the standard deviation, which is 3.526 divided by the square root of the sample size. There's 8 in the sample. And let's calculate that. Equal to 1.25. This is going to be a t-distribution. First of all, I'm working with a sample standard deviation. I don't have the population standard deviation. And my sample size is also pretty small. If I go to the t-table, I will be looking up under column 0.05, and also my degrees of freedom. I'll need that for the row. And that, since we're now working with just one population of differences, is going to be the sample size subtract 1, which is 7. So, going to the t-table under the 0.05 column and 7, I get my t critical value, 2.365, 2.365 on the upper end. Okay, step 3. Let's write a rejection rule. I'm going to reject H sub 0 if t is less than negative 2.365 or t is greater than 2.365, positive 2.365. Step 4, I'm going to calculate my test statistic. So I'm going to take my sample average, negative 0.7375, and I'm going to subtract the what I'm testing against, the 0, and I'm going to divide by the standard error, and I get a negative 0.59. So I'm going to say do not reject h sub 0, since that negative 0.59 indicates that the negative 0.7375 is not in the rejection region. So negative 2.365 is less than negative 0.59 is less than 2.365. So I cannot conclude that there is a difference, although I'm not saying that the null is true. I just don't have evidence to show that there's a difference between the values given by these two methods. Now, another way to look at this, of course, is running the test with a p-value. And if I use the table to do that, I would be under the, again, row 7 with the 7 degrees of freedom, and looking at my test statistic of 0.59, I can see that the value will be greater than 0.20. So I know my p-value would be greater than 0.20, but this is a two-tailed test, so I actually have to double that. And I would indicate from the table that the p-value is greater than 2 times 0.20, which is equal to 0.40. If I used Excel or the calculator to get the p-value, the p-value is actually 0.573, or let's go ahead and look, 0.5727, which is greater than 0.05. So again, do not reject h sub 0. It's too much risk in making a type 1 error. So we are not prepared to say that the null is wrong, and cannot conclude anything really from the test. We can't prove there's a difference in the methods. To avoid type 2 error, are not going to say that the two methods are equal. So that's the conclusion. This is a matched approach to testing the difference between two populations, and there is some notational difference, such as the d bar, and the standard deviation is s sub d, standard error is s sub d bar, and then the population average difference between the methods is mu sub d. We only collected this data that we compared on 8 flights, but we are testing the greater population of all flights and the difference between these two methods on those flights.